Expression trees. Expression tree is a binary tree in which the leaves are operands such as constants or variable names, and the other nodes, that is internal nodes, contain operators. The expression tree for a plus b star c plus d star e plus f star g is shown here. Here the leaf node a, B, C, D, E, F, G are variable names. The other nodes contains operators plus, star, constructing an expression tree. Suppose the input is AB plus CDE plus star star. The first two symbols are operands, so we create one node trees and push pointers to them and to a stack. The first two symbols are A and B, so they are pushed into the stack. The next is plus, so two pointers to the tree are popped out and the new tree is formed and the pointer to it is pushed onto the stack. This is shown. Next, C, D and E are read, and for each one node tree is created and pointed to the corresponding tree is pushed into the stack. Since it is not an operator, we are pushing the symbols into the stack. The next is operator, plus is read. So pop two symbols from the stack and create a subtree. So D and E are popped and creates a subtree. Then the star is read. Again star is the operator, so you have to pop two pointers C and the subtree D plus E and create a tree. Finally the last symbol star is read, so we have to pop two pointers and create a tree. This forms the expression tree. Here all the leaf nodes contains variables, the internal nodes contains operators. Binary search tree ADT. Binary search tree is a tree in which every node X in the tree, the values of all the keys in the left subtree are smaller than the key value in X, and the values of all the keys in the right subtree are larger than the key value in X. For example, here two trees are given. The left side tree is a binary search tree, but the right side tree is not a binary search tree. See here, the root node is 6. Left subtree values 1, 2, 4, 3 are lesser than 6. Right subtree 8 is greater than 6. Likewise, in the left subtree 2. Left of 2 is 1, which is less than 2. Right of 2 is 4 and 3, which is greater than 2. Like in right subtree 4, 3. 4 is greater than 3. So this is a binary search tree. But in the second tree, in the left subtree 2, 1, 4, 3, 7. 7 is greater than 6, so this is not a binary search tree. Implementation of binary search tree. First, the binary search tree declaration. Here, struct tree node. It's a structure for a node. Node contains one value and two pointers. One for left subtree, another one is for right subtree. So, element type element, then tree pointer left, tree pointer right. Then routine to make an empty tree. To make the tree null, search tree make null of returns null. Then find operation for binary search tree. To find an element from a binary search tree, the parameter passed is the element and the tree. So element type X and search tree T. Then if T equal to null means the tree is empty. So it returns null. Then if X less than T element, if the element is lesser than the T element, then we know that the element is present in the left subtree. So using regression, we are calling the find method for left subtree. So find of X comma T left. Else if X is greater than T element, if X is greater than T element, it is present in the right subtree. So we are recursively calling the find method in the right subtree. So find of X comma T right. Otherwise it means that the element is found. So it returns that node. Then recursive implementation of find min for binary search tree. In the binary search tree, the minimum element is present in the left subtree of the last left child. So find min of search tree T. If T equal to null, it means there is no tree. So it returns null. Else if T left equal to null, there is no left subtree, then that value is a minimum element. Otherwise, how to find in the left subtree? So return find min of T left. We know that in binary search tree concept, all the elements lesser than the root node is present in the left subtree. So for finding minimum element, you are searching only in the left subtree. Insertion into a binary search tree. Tree insert of element type X comma search tree T. Here the parameters are element and the tree. After that, if T equal to null means we have to create the tree. There is no tree, so we are creating. For that, using malloc function, we are creating the tree. If T equal to null means there is no space in memory to create tree, so display an error message out of space. After that, in the else part, we are inserting the element T element equal to X. Then the left subtree and right subtree are set as null. After that, if X is the less than the T element, then we have to insert the lesser element in the left subtree. So T left equal to insert of X comma T left. Otherwise, if X greater than the T element, then you have to insert in the right subtree. So T right equal to insert of X comma T right. Then we are returning the tree. This is an example for insertion. We are going to insert 5 in the tree. How to check from root element? Root element is 6. 5 is less than 6. So we have to insert in the left subtree. In the left subtree, root is 2. 5 is greater than the root value. So we have to insert it in the right subtree of 2. So in the right side, right subtree, 4 is root. 4 is less than 5. So we have to insert it in the right subtree. The right subtree is null. So we are inserting there. The pointer is from 4 to 5. The second figure shows the 5 is inserted in the right subtree of 4. Deletion routine for binary search tree. To delete an element from binary search tree, have to pass two arguments, element and the tree. If T equal to null, if there is no tree, we can't find the element and we can't delete the element. So we are displaying error message element not found. Else, if x is less than t element, if x is less than the t element, we have to delete that node from left subtree. Means if x is less than t element, the element is present in left subtree of x. So we are calling the delete method in the left subtree. If x is greater than t element, we are calling the delete method for right subtree. So t right equal to delete of x comma t right. Then after the position of the element is found, we are checking that t left and t right, the element having the left subtree and right subtree. If that element have left subtree and right subtree, then we are finding the minimum of right subtree. So temp cell equal to find min of t right. We are calling the find min method and the minimum values written in the temp cell. So in the t element means the elements we are going to delete. In that position we are inserting the minimum element of right subtree. So temp cell holds the minimum element of right subtree. So the t right delete t element comma t right. Again we are calling the delete method for that element in the right subtree. The minimum element is moved to the position of x, and after that the element is deleted from the right subtree. Otherwise, if the element having only one child, only one subtree, right subtree or left subtree, so if t left equal to null, means there is no left child, so we are moving to right, child equal to t right. If the right subtree equal to null, we are moving to left subtree and we are returning that child. After freeing that element x, you are deleting. Free is used to deallocate the memory space. After deleting, we are returning the tree. Deletion of a node 4 with one child before and after. See, in this tree we are going to delete the element 4. First we have to find the location of 4. 4 is less than the root node 6, so we know that 4 is present in the left subtree. So we are checking only in the left subtree. In the left subtree root is 2. 2 is less than 4, so we know that the 4 is present in the right subtree of 2. So 4 is reached. So from that you are checking that 4 having two subtrees, left subtree and right subtree, or only left subtree or only right subtree. Here 4 having only left subtree. So we have to move that node to position 4 and we are linking to 2 and we are deleting the element 4. The pointer is removed from 2 to 4 and set to 2 to 3. Deletion of the node 2 with 2 children. Here the 2 is present in the left subtree of 6. Here in the 2, the node contains left subtree and right subtree. So we have to find the minimum element from the right subtree. In the right subtree the minimum element is 3. So 3 is moved to position 2. And then the pointer 4 to 3 is removed and we are pointing from 4 to 3.5. Now 3.5 is the left child of 4. Since 3.5 is lesser than 4, it should be present in the left subtree of 4. Applications of trees. Trees are used in operating systems, compiler design and searching. Expression tree, which is used in parse tree representations. Then the search trees are used for algorithm designs. And for traversal, in-order traversal, pre-order, post-order traversal, the trees are used. These are some of the applications of trees. Applications of heaps. Heap is a data structure. It is used for sorting. Then priority queue. Priority queue can be implemented using binary heap. And binomial heap, Fibonacci heap are the variations of the binary heap. It is used to find the kth smallest element in efficient way from the array. These are the some applications of heaps.